lesson, we pick up with a topic on weak bases. Many similarities between weak acids and weak bases in terms of mathematical expression, but remember that when acids ionize, they release the acid ion hydrogen. When bases ionize, they release the hydroxide ion. So weak bases, when they are placed into water, abstract protons, remove protons, steal them away. Let's use a generic letter B for any substance acting as a base. When I place that substance into water, H2O, we set up an equilibrium where the base abstracts the proton from a water, forming its conjugate acid, leaving the hydroxide ion, OH negative. The solution becomes basic due to the hydroxide formation of water. A base, water acting as an acid, forming the conjugate base hydroxide. As with any dissociation, we can express that in terms of an equilibrium constant. The equilibrium constant associated with bases is known as a Kb value, the equilibrium ionization constant for a base. Products over reactants, where the pure liquid of water will drop out. Our expression then for Kb becomes the concentration of our conjugate acid, written as Hb positive 1, times the concentration of our conjugate base, the hydroxide ion, over the original value of our base. Ions over molecule, dissociated over the undissociated form, products over reactants, all saying the same thing. When a base ionizes, hydroxides come out. When acids ionize, hydrogen ions come out. Kb is always referring to an equilibrium in which a base reacts with water to form the corresponding conjugate acid and the hydroxide ion. The conjugate acid, Hb positive, and the hydroxide ion, the base. There are some instances where we have compounds that, through the Bronsted-Lowry definition, are indeed basic, but they don't necessarily end with an OH negative. Bases without hydroxides can very often act as a Bronsted-Lowry acid or a base. Ammonia is a very good example. When ammonia, NH3, is placed into water, it abstracts a proton from water. Think about the Lewis structure of ammonia, with that lone pair of electrons on that nitrogen, making this region very electronegative, a very polar molecule. And water, who is also a polar molecule, with a region that is positive. This hydrogen bond is very easily broken, and here would be the attachment site for that next hydrogen, forming ammonium, NH4+, and leaving hydroxide, OH- in equilibrium. If ammonia takes off a hydrogen ion from a water to fill up that electron octet up here, it leaves a hydroxide ion in solution. So it's this lone pair of nitrogen that accepts the proton. Many weak organic bases contain nitrogens. This is a compound known as an amine group in organic chemistry. NH2 with a hydrocarbon chain, so some long hydrocarbon chain connected to an NH2 group, is a functional group known as amine. You can hear that base word in the word ammonia. We know that strengths of bases vary, just as the strengths of acids vary. And we know that from our helpful tool page listing the strong bases down to the weak bases. Of course, there are bases that 100% dissociate and are considered strong. Those strong bases 100% dissociate. We know those strong bases would ionize completely in water. The strong bases come from the first family, such as lithium hydroxide, sodium hydroxide, potassium hydroxide, rubidium hydroxide, and cesium hydroxide. Those alkali metals 100% dissociate. These strong bases do not have a Kb value. The heavy metals of group 2A, such as strontium hydroxide and barium hydroxide, 100% dissociate and would not have a Kb value. Just as we had 7 strong acids to memorize, knowing that they 100% dissociate, and to calculate their pH, we do so directly. We do not need an equilibrium concentration. The same is true for these strong bases. The alkali metals and the heavy metals of the first family 100% dissociate. Ammonium hydroxide would also fall into that. Ammonium ions would 100% dissociate. All other bases are weak and have a Kb value. The Kb values on our test-taking tool page of Appendix D, notice there's all kinds of acids listed for us, and if we flip over, there's a small appendix here on the back side of our test-taking tool page that gives us an examples of Kb values for bases. Ammonia as a base has a Kb of 1.8 times 10 to the negative fifth, and so forth. Notice here that many of these organic bases end with nitrogen. Every one of these, as a matter of fact, contains nitrogen as its source of being basic. Let's take a look at an example problem. If I flip over, and I can try to get that on the screen a little bit better, an example problem where we're being asked to calculate the solution of a pyridine. Now, pyridine is a nitrogen-based base. Let me kind of draw that for you. I want to suggest to you the importance of the nitrogen. Pyridine is a 6-sided aromatic ring that contains nitrogen as one of its bases. So draw a 6-sided ring and place nitrogen and alternate the double bonds. That lone pair of electrons on the top of pyridine abstract a proton when placed into water. Right here is the cleave of this bond, and hydrogen goes on to form the conjugate acid of pyridine, NH positive, leaving the base OH negative. Pyridine is an aromatic hydrocarbon that acts as a base. Amines are organic bases whose functional group contains nitrogen. Perhaps you heard, if you've had anatomy, physiology, or biology class, amino acids. Amino acids are the basic building block of proteins. Anyway, I wanted to emphasize nitrogen-based compounds acting as bases with that electron cloud on top of the nitrogen, very capable of pulling off a proton from the water. If we're being asked to calculate the pH of a solution that's acting as a base, remember to think about the chemistry. Pyridine representing our sample of a base. Now, instead of writing out the formula for pyridine, I'm going to let B represent my pyridine structure. And I place that into water, and pyridine is able to abstract the proton. It will form a conjugate acid and the base ion hydroxide. Let's let B stand for any weak base. It will always follow the same chemistry. We're given a 4.0 molar pyridine solution and the Kb of niacin. Niacin is listed as 1.7 times 10 to the negative ninth. Water, of course, drops out of our equilibrium expression. Let's let the value of X stand for the base ion hydroxide and the conjugate acid BH positive. Kb of 1.7 times 10 to the negative ninth, set equal to X squared, where X stands for base ion, set over the original value of 4.0 molar. Let's pull out X, knowing X represents the base ion. 1.7 E negative 9 times 4 represents Kb times molarity, represents X squared, square root your answer, and X comes out to be 8.25 times 10 to the negative 5th molar units. When I negative log 8.25 times 10 to the negative 5th, we get something called POH. The hydroxide ion concentration negative logged gives us POH. So negative log our answer, and the POH is 4.08 units. Don't forget to flip that to a base. The pH of a base is higher than 7. 14 minus our answer, and we find 9.92 pH units of our pyridine solution. See the extra step involved compared to a weak acid? Weak acids, we let X stand for hydrogen ion, negative log directly, and we add pH. But with a weak base, X is standing for the base ion, so when we negative log that value, we get POH. 14 minus that flips it back to the pH unit. One last little step there compared to the weak acids. Let's calculate the concentration of hydroxide ion in a 0.15 molar solution of ammonia. Do the chemistry. Ammonia is a weak base, NH3. When placed into water, it ionizes to create a conjugate acid, ammonium, and the base ion, hydroxide. Notice our general formula will always carry us through. Ammonia, they're not giving me, so I have to pull out my appendix D here and find ammonia. Ammonia Kb, 1.8 times 10 to the negative 5th. Not provided this time, so we had to look it up. 1.8 times 10 to the negative 5th, the Kb of ammonia. So if the original solution was 0.15 molar, letting the X stand for the hydroxide concentration and also the conjugate acid concentration, we have X squared on the top over 0.15. Let's pull out X, knowing that that represents hydroxide concentration. (1.8 E negative 5 times 0.15 is X squared. Square root that answer, and we get X. 0.0016 molar units, the value of our hydroxide concentration. And if I notice that's all it asked me to do, I could negative log, find POH, and flip it to pH. But this problem only asks us to find the concentration of hydroxide, the value of X. And so we're done with that one. Sometimes salts will create acids and bases. We can use pH to determine the concentration of a salt. The salt of sodium hypochlorite. Now I stressed earlier in the lessons about the spectator ions of any first family metal. If I take a solution and add a solid salt to it, that first name, sodium or any other first family metal, will drop out. It is a spectator ion. So when I look at this sodium hypochlorite, which is, by the way, bleach, NaClO, remove the sodium and you'll find the interesting chemistry for acids and bases. It's the hypochlorite polyatomic ion that when reacts with water creates a conjugate acid and the conjugate base. We place that into 2 liters and it ends up with a solution of 10.5 pH units. The chemistry eliminating sodium shows the hypochlorite extracting a proton from water, creating its conjugate acid, hypochlorous acid, with the hydroxide conjugate base. Calculate the number of moles of sodium hypochlorite that were added to the water. Well, let's go to work recording what we know. The pH is 10.5. But more interesting to us in base chemistry would be the pOH. Knowing the pOH, I could calculate hydroxide. 14 minus 10.5 tells me the pH is 3.5. Of course, 10 raised to the negative 3.5 will pull out the value of hydroxide ion concentration. So let's take our 10 raised to the negative 3.5, 10 raised to the negative pOH, and we find the hydroxide value to be 3.16 times 10 to the negative fourth molar units. The concentration of hydroxide, 3.16 times 10 to the negative fourth. And not only is it the hydroxide concentration, but it's also the conjugate acid concentration. Those two values are always equivalent, seeing that we end up with the same amount on both sides. The Kb value was given as 3.3 times 10 to the negative seventh. We know the concentration of hydroxide, 3.16 times 10 to the negative fourth. And since that's the same value for the hypochlorous acid, the HClO, let's just square the top instead of writing that number twice. What we don't know is the concentration of the hypochlorite. Let's make that the value of X. Let's pull out X, and what X represents is the concentration of the hypochlorite. Now, key sequence would have X and the Kb just exchanging places. So the key sequence would have us take 3.16 E negative 4 squared, squaring that, dividing by Kb. Now remember, these two algebraically just exchange places, so I'll divide that by 3.3 E negative 7. And I get a value of X as 0.303 molar. Moles, or molarity, is moles per liter. Remember, we're being asked, calculate the number of moles. Well, how many liters did we have? Oh, right here, 2 liters of solution. So if 0.303 molarity is the concentration of a 2-liter solution, let's just cross multiply, so go times 2, and the number of moles is 0.605 moles of sodium hypochlorite. Here's what we've done. We used pH to find pOH of a basic solution. The pOH allowed us to calculate hydroxide's concentration. 10 raised to the negative pOH is giving us this concentration of the base ion. But it also gives us the conjugate acid. These two are always equivalent. So I squared the top, set it over my target variable X, and the given Kb value. Pulling out X, the molarity of our ClO negative hypochlorite, we were able to cross multiply with the volume and end with the number of moles of our sodium hypochlorite, 0.605 or 0.61 moles of NaClO. We'll do one more together. If a solution of ammonia, NH3, or simply the letter B for base, setting up an equilibrium with water, the base extracts a proton, forming a conjugate acid, ammonium, and the conjugate base, hydroxide. What's the molarity of our solution? So the previous problem asked us to go to moles. This time we're only being asked to go as far as molarity. But pH would tell us the concentration of hydrogen ions. We want to know pOH to determine hydroxide concentration. 14 minus the pH of 11.17 is 2.83. The pOH of our solution, 2.83 units. 10 raised to the negative 2.83 pulls out hydroxide. Let's hit 10 raised to the negative 2.83, and we get 0.00147. You want to say 0.0015? That's the concentration of the hydroxide. The concentration of hydroxide is also that of the ammonium. The conjugate acid and conjugate base are equivalent values. Now we'll need a Kb, not provided, so we go to work and just look it up. 1.8 times 10 to the negative fifth, the Kb for ammonia. Set that equal to the concentration of the base ion, 0.0015, times the concentration of the conjugate acid, so we'll just square the top and make the bottom our target, letting X stand for the concentration of ammonia in molarity units. The algebra has the X and the Kb value. Simply exchange places. So to hit out, we get 0.0015 squared divided by 1.8 e negative 5. In the concentration of the ammonia, 0.125 molar units. 0.125 molar, the concentration of ammonia in our equilibrium. With our weak bases, we turn pH into pOH. 10 raised to the negative pOH pulls out the concentration of hydroxide, which is also the concentration of the acid, the conjugate acid. Square the top, set it over your target variable, and set that equal to the looked up value of Kb for ammonia. Pulling out X, solved for 0.125 molar units. At this point, we have enough ammunition to do well on assignment 6. Due for tomorrow, assignment number 6 off of our chapter 16 lesson page. Let's go to work.